The National Electrical Code, or NEC, permits a diversity factor of 0.75 for dwellings, apartments, hotels, and motels. However, for other occupancies, the diversity factor must be determined by the engineer in accordance with Article 220.42b of the NEC. The diversity factor of 0.38 for the yacht club implies that the actual load is only 38% of the calculated load. This is a significant departure from the NEC assumption of 0.75 for residential occupancies. The NEC does not specifically address the use of past performance or data logging to justify a reduced conductor size. However, the authority having jurisdiction, or OJ, may allow such evidence to be considered in determining the appropriate diversity factor. Based on the information provided, the two options available are firstly, historical performance, that is, provide evidence that the transformer has never been overloaded for the past 10 years. The AHJ may consider this evidence along with other factors to justify a reduced diversity factor. Secondly, data logging. Conduct a data logging study to measure the actual load over a period of time. The data collected can be used to calculate the actual diversity factor and demonstrate that the calculated load is excessive. The NEC does not explicitly permit the use of actual load data to justify a reduced conductor size. However, the AHJ may allow such evidence to be considered when determining the appropriate diversity factor. The yacht club can explore either historical performance or data logging to support their request for a reduced conductor size. Article 220.42b allows for the application of a demand factor or the use of calculations that provide a more accurate estimate of the load than the standard calculations. This means an engineer can use their expertise and judgment, supported by data and analysis, to determine a more suitable diversity or demand factor for the specific installation. Several factors should be considered. Firstly, the nature of the loads. Understand the types of electrical loads present, such as lighting, HVAC, refrigeration, and various appliances. Categorizing the loads helps in estimating their individual and combined demand. Secondly, load characteristics. Analyze the operational characteristics of each load. This includes whether they operate continuously, intermittently, or cyclically. For example, lighting might be continuous while HVAC cycles on and off, and appliances might be used intermittently. Thirdly, occupancy patterns. Evaluate how the facility is used over time. Consider daily, weekly, and seasonal variations in occupancy. This helps in understanding when peak demands are likely to occur. Fourthly, load diversity. Assess the diversity of the loads, that is, the extent to which different loads operate simultaneously. If loads operate at different times, the overall demand will be lower than the sum of their individual demands. Fifthly, historical data. Review historical energy consumption data, if available, to identify trends and patterns in electrical demand. This data can provide valuable insights into actual usage and demand. Sixthly, manufacturer's data. Obtain manufacturer's data for the equipment being used, including their power consumption and operating characteristics. This information can help in accurately estimating the demand of individual loads. Seventhly, engineering judgment. Apply engineering judgment and experience to assess the interactions between different loads and their combined effect on the overall demand. This involves considering factors such as load shedding, peak shaving, and energy management strategies. The process for obtaining approval for reduced conductor sizing based on actual load data involves several steps. Firstly, conduct a load study. Perform a detailed load study to measure and analyze the actual electrical demand of the facility. This study should include monitoring and recording the current and voltage levels over a representative period, typically several weeks or months. Secondly, data analysis. Analyze the data collected during the load study to determine the maximum demand and the diversity factor. This analysis should be performed by a qualified electrical engineer. Thirdly, engineering report. Prepare a comprehensive engineering report that documents the load study, data analysis, and proposed conductor sizing. The report should clearly justify the reduced conductor size based on the actual load data and provide supporting calculations and diagrams. Fourthly, submission to the AHA. Submit the engineering report to the AHA for review and approval. The AHA may require additional information or clarification before making a decision. Fifthly, AHA review. The AHA will review the engineering report and may conduct a site visit to verify the accuracy of the data and calculations. They may also consult with other experts or stakeholders before making a decision. Sixthly, approval and documentation. If the AHA approves the reduced conductor sizing, obtain written documentation of the approval. This documentation should be kept on file and made available for future inspections. Several potential challenges may arise during the process, and it's important to be aware of them. Firstly, data accuracy. Inaccurate or incomplete data can undermine the credibility of the load study and engineering report. Ensure that the data is collected using calibrated instruments and that all relevant loads are accounted for. Secondly, AHA acceptance. The AHA may be reluctant to approve reduced conductor sizing based on actual load data, especially if it deviates significantly from the NEC standard calculations. It may be necessary to provide additional evidence or clarification to address their concerns. Thirdly, future load changes. Changes in occupancy, equipment, or operations can affect the electrical demand of the facility. It's important to consider the potential for future load growth when determining the appropriate conductor size. Fourthly, liability. In the event of an electrical failure or safety issue, the engineer and facility owner may be held liable if the conductor sizing is found to be inadequate. Ensure that all calculations and decisions are made in accordance with accepted engineering practices and standards. Here are some strategies for addressing these challenges. Firstly, thorough data collection. Invest in high-quality data logging equipment and ensure that the data is collected accurately and completely. Calibrate instruments regularly and verify the data for consistency and accuracy. Secondly, clear communication. Communicate clearly and effectively with the AHA throughout the process. Address their concerns and provide them with all the information they need to make an informed decision. Thirdly, conservative approach. Take a conservative approach to conductor sizing, even when using actual load data. Consider the potential for future load growth and factor in a safety margin to account for uncertainties. Fourthly, documentation. Maintain thorough documentation of the load study, data analysis, and engineering calculations. This documentation can be used to support the reduced conductor sizing and demonstrate compliance with applicable codes and standards. Here are some additional considerations to keep in mind. Firstly, NEC requirements. Familiarize yourself with the specific requirements of the NEC regarding conductor sizing and demand factors. Understand the limitations and exceptions that may apply to your situation. Secondly, industry standards. Refer to relevant industry standards and guidelines for conducting load studies and determining demand factors. These standards can provide valuable guidance and best practices. Thirdly, peer review. Consider having the engineering report and calculations peer-reviewed by another qualified electrical engineer. This can help identify any errors or omissions and ensure that the proposed conductor sizing is safe and reliable. Fourthly, insurance requirements. Check with your insurance provider to ensure that the reduced conductor sizing will not affect your coverage. They may have specific requirements or recommendations regarding electrical installations. The NEC provides tables and guidelines for determining the ampacity of conductors based on their size, installation type, and installation conditions. These tables are used to ensure that conductors can safely carry the intended load without overheating. Article 310.15 of the NEC provides guidance on determining the ampacity of conductors. It references various tables such as Table 310.15. B16, which lists the allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius in free air and various raceway types. These ampacities are based on specific conditions, such as the number of conductors in a raceway or cable, the ambient temperature, and the conductor's insulation temperature rating. Correction factors are applied to adjust the ampacity for conditions that differ from the base conditions specified in the tables. These factors account for things like higher ambient temperatures or more than 3 current-carrying conductors in a raceway. The NEC also provides guidelines for derriting conductors when multiple current-carrying conductors are installed in a raceway or cable. This derriting is necessary to prevent overheating due to the combined heat generated by the conductors. The derriting factors are specified in Table 310.15. The 3 conductors must be sized to handle the non-continuous load plus 125% of the continuous load. This ensures that the conductors can handle the sustained load without overheating. Continuous loads are defined as loads that operate for 3 hours or more at a time. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overloads and short circuits. The overcurrent protection device must be sized to protect the conductor while allowing it to carry its intended load. The NEC provides guidelines for selecting the appropriate overcurrent protection device for a given conductor size. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Conductors must be sized to minimize voltage drop and ensure that equipment receives adequate voltage. The impedance of a conductor is its opposition to the flow of alternating current. Impedance is affected by the conductor's resistance, inductance, and capacitance. The NEC provides formulas for calculating the impedance of conductors. The reactance of a conductor is its opposition to the flow of alternating current due to its inductance and capacitance. Reactance is affected by the conductor's size, spacing, and frequency. The NEC provides formulas for calculating the reactance of conductors. The skin effect is the tendency of alternating current to flow near the surface of a conductor. The skin effect increases with frequency and conductor size. It can reduce the effective ampacity of a conductor. The NEC provides guidelines for accounting for the skin effect when sizing conductors. Harmonics are currents or voltages that are multiples of the fundamental frequency. Harmonics can cause equipment to overheat and malfunction. The NEC provides guidelines for mitigating the effects of harmonics in electrical systems. Grounding is the process of connecting electrical equipment to the earth. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. The NEC provides detailed requirements for grounding electrical systems. Bonding is the process of connecting different metal parts of an electrical system together. Bonding ensures that all metal parts are at the same potential, which helps to prevent electrical shock. The NEC provides detailed requirements for bonding electrical systems. Surge protection devices are used to protect electrical equipment from voltage surges caused by lightning or other events. Surge protection devices divert the surge current to ground, which prevents it from damaging the equipment. The NEC provides guidelines for selecting and installing surge protection devices. Energy efficiency is the measure of how efficiently electrical energy is used. The NEC promotes energy efficiency by requiring the use of energy-efficient equipment and practices. Power quality is the measure of the quality of electrical power. Poor power quality can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for improving power quality in electrical systems. Maintenance is the process of keeping electrical equipment in good working order. Regular maintenance can help to prevent equipment failures and ensure that the electrical system operates safely and efficiently. The NEC provides guidelines for maintaining electrical systems. Safety is the most important consideration in any electrical installation. The NEC provides detailed requirements for ensuring the safety of electrical systems. The NEC is constantly evolving to keep pace with new technologies and safety concerns. It is important to stay up to date on the latest requirements of the NEC. The NEC is enforced by local authorities, such as building inspectors and electrical inspectors. These authorities are responsible for ensuring that electrical installations comply with the NEC. The NEC is a complex and comprehensive document. It is important to consult with a qualified electrical professional when designing or installing electrical systems. Electrical work can be dangerous. It is important to take precautions to protect yourself from electrical shock. Always turn off the power before working on electrical equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. Never work on electrical equipment when you are wet or standing in water. If you are not qualified to perform electrical work, hire a qualified electrical professional. The electrical system is a critical part of any building. It is important to ensure that the electrical system is properly designed, installed, and maintained. A properly designed and maintained electrical system will provide safe and reliable power for years to come. The NEC is the cornerstone of electrical safety in the United States. By following the requirements of the NEC, you can help to ensure the safety of yourself, your family, and your property. Understanding the NEC is essential for anyone involved in the electrical industry. Whether you are an electrician, engineer, inspector, or homeowner, a solid understanding of the NEC will help you to make informed decisions about electrical safety. The NEC is a living document that is constantly being updated and revised. It is important to stay informed about the latest changes to the NEC so that you can ensure that your electrical installations comply with the current requirements. The NEC is available for purchase from the National Fire Protection Association, or NFPA. You can also find information about the NEC on the NFPA website. The NEC is a valuable resource for anyone who wants to learn more about electrical safety. By taking the time to study the NEC, you can become a more knowledgeable and informed electrical professional or homeowner. Remember that electrical work can be dangerous. Always take precautions to protect yourself from electrical shock. If you are not qualified to perform electrical work, hire a qualified electrical professional. Your safety is worth it.